Hello, everyone. I hope everyone's having a good night. Or in this case, morning. It's night for me. Sorry about the bad lighting, but it's late out here. And today we are going to be talking about atoms. And let's start by let's draw the Bohr model of aluminum. And remember that if we go to the periodic table, our electron configuration is right there, down here, right? 283. 13 protons, and we'll run that up to 27, so that's 14 neutrons. So let's go ahead, we'll give it 13 protons, give it 14 neutrons, and let's give it some electrons. Might have to erase that because I might need more room. Oh, there are 2 electrons there. We know that, what was that? Not the best circle in the world. 8 electrons there. We know there are 2 electrons there. Actually, I want to try something. Hey, look at that. 2 electrons there. Okay. Now, we know that the Bohr model has all subatomic particles, all the electrons, all the neutrons, all the protons. However, when atoms chemically bond, it's really only the valence electrons that are involved. And because of that, we have a special way of drawing the model that doesn't include the protons and the neutrons and all of those core electrons, right? Just so in case you forget, remember that the inner electrons are called core electrons, and the outermost electrons are the valence electrons. So instead of looking at the whole model, if we only want to look at just the outermost electrons, we have a very special type of model, and we can call it the Lewis dot model. Or actually, it's Lewis dot structures. It's the other term for it. And it really only involves 2 things. It only shows the chemical symbol and the valence electrons. So for Al is going to look something like this. Or for aluminum, an atom of aluminum, Al. Oop, sorry, let's move that down a little bit more and you'll see why. Aluminum. So there we go. 3 valence electrons and just the symbol. For elements that have 8 valence electrons, which have a very special way of drawing the Lewis dot structure. Now, you don't have to draw it this way. I'm going to always draw it this way, but you don't have to. So, for an element with up to 8 valence electrons, and really we're not going to worry past 8, so don't worry about it. There's a very special way. So symbol, we're going to give symbol X, just making it up. And here's how we always draw it. 1, 2, 3, 4, 5, 6, 7, 8. In case you missed that, we'll do it one more time. 1, 2, 3, 4, 5, 6, 7, 8. So that's how I'm going to always draw it. You don't have to draw it that way. So that's a Lewis dot structure. Now, let's take a look at the periodic table. Now, I want to focus on just the noble gases for a second. Noble gases, right? If we look at noble gases, we know that they're all in group 18. They're all in the same group, right? And we can see that they all have, besides helium, they all have 8, 8, 8, 8, 8 valence electrons. Not only that, but let's take a look at some of our ions, right? Potassium. Potassium forms a +1 ion. If it were to lose its +1 ion, its electron configuration would be 2, 8, 8, right? So potassium +1, its electron configuration 2, 8, 8. Let's look at another example. Let's look at, I don't know, strontium. Sr. It happens to lose 2, right? It says it's going to form a +2. Give it an electron configuration of 2. What was it? Ah, look at that. 2, 8, 18, 8. Huh. Sorry, +2. Aluminum. Aluminum forms a +3. Look at that. 2, 8. When its electron configuration for the ion is 2, 8. Let's keep on going. Fluorine. Fluorine forms a -1. We add 1 to that valence shell. 2, 8. Oop. Let's do one more. Let's do phosphorus. That tends to form a -3. If phosphorus formed a -3, 2, 8, 5, 5 plus 3 is, oh, look at that, 8. 2, 8, 8. Notice how there's this pattern of having the same valence electrons as the noble gases. There is a pattern. Of having 8 valence electrons when you form an ion, and we remember that the noble gases, look at that, doesn't form an ion. Doesn't form an ion. Can form an ion, not really. It gets more unstable down here, but like no ion, right? And that's because there's a very special rule in chemistry for stability. And we call this rule the octet rule. Now, I'm calling it the octet rule because it is a rule. However, it's more of a trend than an actual rule. And basically, the octet rule says that elements are very stable when they have a valence shell of 8 electrons. So 8 electrons tends to be very stable. It's something in nature that we see over and over again. And there's a very special reason for it. It has to do with the fact that if you think about it, how many total electrons can fit in the second shell? 8, right? Has to do something with how the second shell is made and its stability, right? Now, there are 2 exceptions to this rule, or a couple exceptions to the rule. Exceptions, and I apologize for my spelling, to the rule, and that has to do with lithium, helium, hydrogen, and all that, right? So notice lithium and beryllium, and boron, kind of, carbon not so much, but lithium and beryllium definitely. They become ions, and they're only going to have 2, right? They're only going to have 2. Hydrogen, if it becomes an ion, it's going to have 2. Helium has 2. So we remember that really anything dealing with a valence of the first shell. So the exception to the rule is based on the first shell. Remember that shell can only hold a maximum of 2 electrons, right? So what we're going to do now is we're going to practice drawing Lewis dot structures. And remember, and I read over this already, but remember that metals lose electrons when they become ions. So let's start with drawing, I don't know, the calcium Lewis dot structure. So this is the atom. And we can see over here that if it has 2 valence electrons, metals tend to lose to get that 8, right? It's going to lose those 2 valence electrons to get that 8. So for a calcium ion, we would draw it like this. Ca plus 2. Very important. Must always draw in the charge whenever you're drawing an ion, because otherwise it doesn't look right. Now, you will notice that there's nothing around it, right? There are no dots around it. Why are there no dots around it? It's because Lewis dot structures always refer to the valence shell of the parent atom. So calcium's valence shell as an atom is the 4th one, right down there, right? So valence shell is the 4th shell. So whatever ion calcium would make, we draw the Lewis dot structure with the reference of the 4th shell, which is why over here we're not drawing any dots. It's not that it doesn't have any electrons, okay? Now, some new vocab. We call positive ions, we call them, there are 2 ways to spell it. That's either cation or cation. Why or how do you remember? It's because it is positive, like a cat. Meow. It's positive, so it's a cation. So all positive ions are called cations, okay? And then, of course, we remember that nonmetals tend to lose. Tend to gain electrons. And it's very important to note that up here, I wrote metals lose electrons. And down here I wrote nonmetals tend to gain. Why did I write that? Because we can see here that wherever you're looking, all of these metals, no matter what metal you look at, they're always going to form positives. Nonmetals, only sometimes. Only occasionally, right? Iodine has a whole bunch of them, and apparently most of them are positives. So nonmetals tend to gain electrons when becoming ions. Okay, and let's look at an example. Let's look at an oxygen atom. 1, 2, 3, 4, 5, 6. So this is the atom. And then to fulfill the octet rule, it has to gain 2 electrons. 1, 2, 3, 4, 5, 6, 7, 8. And what we're going to do is we're going to give it a bracket and a -2. And the reason we give it a bracket, the bracket shows that the O owns, quote unquote, owns the electrons. Now, we don't really need that now, but we will need that when we start talking about chemical formulas in a little bit. Okay? And finally, we have a very special name for negative ions. And we call these, negative ions are called anions. And I remember that as an negative ion. Anion. It's a negative ion. And that is your little introduction to Lewis dot structures and ions. I hope everyone has a good night. Bye.